So in this video we're going to go over electromagnetic induction, but first I'm going to review the concept of magnetic flux. So the magnetic flux through a surface is defined as the integral of the magnetic field dot product, the dA, which is the area vector or the normal vector. And so this is the same definition as electric flux, which remember was E dot dA. So it's the same concept, and the unit of magnetic flux, it has a special name called the Weber, which as you can see is Tesla times meter squared, because we have the magnetic field times an area. And so unlike the electric flux, which we've had Gauss's law, which said that the electric flux through a closed surface is always equal to the enclosed charge divided by a constant. Well, here the total magnetic flux through a closed surface turns out to be always zero. And this is because there are no magnetic monopoles, which means we can't have a magnet with a north pole but not a south pole. Every magnet has a north and south pole. And remember, magnetic field lines from a magnet, they exit the north pole and go into the south pole. So if we have a closed surface around this magnet, all of the magnetic field lines that exit the north pole must also enter the surface again through the south pole. So the total magnetic flux through the surface will always be zero. And this is represented mathematically as the integral of B dot dA is equal to 0 over a closed surface, which is what this circle means. Okay, so now let's talk about electromagnetic induction. So it turns out if we have a circuit and there is a changing magnetic flux through that circuit, then it can induce an EMF, which in turn causes an induced current. And so Faraday's law says that the induced EMF in a closed loop is equal to the negative time rate of change of the magnetic flux, which is the derivative of the magnetic flux. So again, there's only an induced EMF when the magnetic flux is changing through the circuit. So the instant that the magnetic flux becomes constant or disappears, the induced EMF will also disappear. It's only there when the magnetic flux is increasing or decreasing. And so there are two general cases in which the magnetic flux through a circuit is changing. We can either have a stationary conductor and then the magnetic field through that conductor is changing over time, or we can have a conductor which is moving through a non-uniform magnetic field. So we're going to look at both of these cases later. So you can find the direction of the induced EMF or current using a bunch of sine rules, but we're going to look at an easier rule to use later. So if we have a coil of wire with n identical turns, then to find the induced EMF by Faraday's law, we just multiply it by n, the number of turns. So let's look at a quick example here. We have a 500 loop circular coil with a radius of 4 centimeters, and it's in a uniform magnetic field, which is decreasing at 0.2 Tesla per second. And it makes a 60-degree angle with the plane of the coil. So this is a case of a stationary conductor, and then the magnetic field through the conductor is changing over time. So since the field is uniform, the magnetic flux we can write as BA cosine theta instead of the integral of B dot A cosine B dot A. And so by Faraday's law, we need to calculate the time derivative of the magnetic flux, which is the same thing as the derivative of BA cosine theta. And well, the area of the loop and cosine theta are both constant, so we can take them out of the derivative. So the derivative of the magnetic flux is the same thing as A cosine theta, times the time derivative of B, the magnetic field. And we know that is negative 0.2 since that's how fast it's decreasing. So now we just use Faraday's law, including the number of coils, and plug everything in. And we want to use 30 degrees for this angle theta, not 60, because this angle is supposed to be the angle between the area vector and the magnetic field vector, which is 30 degrees in this case. So calculating those, we find that the induced EMF is 0.435 volts. So now we're going to look at how to determine the direction of the induced EMF and current. And so we can use something called Lenz's law, which says that the direction of any induced EMF or induced current is going to oppose the original cause of this effect, whatever caused the induced EMF in the first place. So first let's look at changing magnetic field through a stationary conductor. So the induced current that the induced EMF causes is going to set up its own magnetic field. Of course, when we have a current through a conductor, it creates a magnetic field of its own. So this magnetic field that it creates is going to oppose the change in the flux which caused the induced EMF originally. So here we have a picture of a circular conductor, and the cause of the induced EMF in this case, we see there's a magnetic field pointing upwards, and this magnetic field is increasing, which of course causes the flux to change, and then the EMF is induced. So Lenz's law says that the induced current is going to try to oppose this increasing magnetic field which caused the induced EMF. So using the right-hand rule, we can determine that the induced current must be going clockwise. Since if the current is clockwise, it's going to set up its magnetic field pointing downwards, which is going to combat this increasing upwards magnetic field. If instead of an increasing magnetic field, we had a decreasing magnetic field which is still pointing upwards, so it's pointing upwards but it's getting smaller, and that's causing the induced EMF, then the current will be set up in the opposite direction, counterclockwise. And that way, the induced current sets up its magnetic field so that it's pointing upwards to oppose the decreasing magnetic field. So it's trying to kind of delay whatever the original cause of the effect was. Now, in the case of a moving conductor through a magnetic field, then the direction of the induced current in the circuit is going to try to, again, oppose the original effect, which in this case is the velocity of the moving conductor. So here we have this circuit, and a conducting burr is moving to the right, sliding along these wires. So the magnetic flux is changing because the area of the circuit is changing, not the magnetic field, but the area, which is a part of the magnetic flux equation. So the cause of this induced EMF is the velocity of this moving burr. And so the current is going to set up so that it creates a magnetic force on this conductor, which is going to point to the left, opposing its original motion. And again, you can test all this with the right-hand rule.